and we can move to the next speaker, which is Emil Karlsson, who will talk about the strengthening of feasibility cuts in logic-based standards composition. So, Emil, when you want.
Hi and welcome. My name is Emil Karlsson, and I'm here today to talk about the strengthening of feasibility cuts in logic-based benders decomposition. This is joint work between me and my PhD supervisor, Elina Rönnberg, both of us from the Department of Mathematics, Linköping University in Sweden. I'm also associated with Saab. Today's talk is about the comparison of cut strengthening algorithms, particularly the strengthening of feasibility cuts in the context of logic-based benders decomposition. First, we go into a bit about the framework of the logic-based benders decomposition that we do this cut strengthening on, and some of the problems that we work on. Then we dig a bit deeper into the strengthening of feasibility cuts, and finally we talk about the computational evaluations that we have made as part of this work. The logic-based benders decomposition framework that we apply in this paper looks as follows, where x denotes the master problem variables and y denotes the subproblem variables. We let the domain for a set of variables x be denoted with dx, and the constraints for a set of variables x be denoted as c of x. Typically, when you want to apply some sort of decomposition approach, you have some problem structure that you want to take advantage of or exploit. So also in this case. So the problem structure that we assume is that the master problem variables are binary. We assume that the objective function only depends on x. And further, finally, we assume a specific structure between the connection of the master problem variables and the subproblem variables, what is denoted as c of x and y in the logic-based benders framework showed earlier. This specific structure is such that if a master problem variable xi is assigned to 1, there is a specific set of constraints ci of y that is included in the subproblem. But if the master problem variable is assigned to 0, there is no impact on the subproblem at all. And this holds for all the master problem variables in this decomposition. And what we want to do is that we want to test of different cut strengthening algorithms taken from the literature on 3 problems that has this structure. So the first problem that we test on is called single machine scheduling with the multiple time windows and sequence dependent setup times. For this problem, there is a known decomposition where the master problem is about collecting prices from assigning tasks. So a price is collected when a task is assigned to one of its time windows. The subproblem then becomes, can the assigned tasks be scheduled within their time windows? The second problem is called cumulative facility scheduling with fixed costs. And in this case, instead of having a single machine, we have a set of facilities and a set of tasks that must be performed on these facilities. So the master problem here becomes that each task must be assigned to a facility, and we want to minimize the total assignment costs. The subproblem then becomes, can the tasks be scheduled at their assigned facility? And we can have a separate subproblem per facility if we choose to. The third problem is called vehicle routing with location congestion. And in this case, we have a start and end node, which is colored green here on the illustration, where we originate with a set of vehicles. And the vehicles should perform a number of deliveries, the blue dots, and the deliveries can occur at different each delivery occurs at a different location, but there can be multiple deliveries at the same location, and therefore we have the location congestion issue that we have to deal with. So the master problem here is to assign routes such that each delivery is completed. And we want to minimize the total travel time of the vehicles. The subproblem then becomes, can the deliveries be completed in time, given these routes? So if we go back to the framework, we assume some pieces about problem structure, which is the boxes here. But we can choose to rewrite this to get it a little more straightforward. So first rewrite is to change the objective function to only depend on the master problem variables. The second one is to include the constraints ci of y if a master problem variable xi is assigned to 1. This is shown by the implication here, where I also denotes the set of master problem variables. And the third part is that we have the binary master problem variables. The benefits that we get from this problem structure is that we have feasibility subproblems only, and it's also true that feasibility cuts are sufficient to gain convergence of this scheme. And third, only the x variables actually assigned to 1 is needed in the feasibility cut. If we look at the master and subproblem, and first with the master problem in iteration k, it looks as follows, where bk of x is the set of feasibility cuts. But we can also choose to strengthen the master problem with a subproblem relaxation, as shown here. We let the solution to this master problem, iteration k, be noted with bar x of k. The subproblem then becomes a feasibility problem that depends on the master problem variables, and particularly the solution in a specific iteration. For the general subproblem, we include the constraints cy and also the ci of y for the master problem variables xi, which are equals to 1 in the solution that we look upon, and also the y constraints in their domain. But later, when we want to refine our feasibility cuts, we actually change this ik here to be a subset, or it couldn't be a subset when we want to refine our feasibility cuts. So the feasibility cuts can be written on this form, where a change in one of the x variables assigned to 1 is sufficient to obey this cut. If we look at strengthening of feasibility cuts in more general perspective, it is a common technique to strengthen logit-based Bendis decomposition and to accelerate it. It relies on solving additional sum problem where x, the master problem variables, has been partially assigned. Here it is denoted with a capital I, the blue I here, which must be a subset of the ik, which was the set of master problem variables for a given master problem solution k that are assigned to 1. And this shows to the right because to find cuts we need to solve the subproblem. But if the subproblem sp of I becomes infeasible, we have a feasibility cut on the form down to the right. That depends on actually a fewer number of master problem variables than the original feasibility cut. The algorithms for refining such cuts and selecting the subsets to evaluate is closely connected to the algorithms for finding infeasible irreducible subsets of constraint, or IISs. If we look a bit at the algorithm flow for this type of decomposition in general, it first starts with solving a master problem. If the master problem is infeasible, we have a proof of infeasibility. But if the master problem is feasible, then we can use it to fix certain decisions before entering the subproblem. The subproblem, as I said earlier, is of feasibility type, given this problem structure. And if the subproblems are feasible, then we have arrived at an optimal solution to this instance. But if the one or more of the subproblems are infeasible, then we have feasibility cuts that we can add. And then we resolve the master problem to get the new solution and the new iteration of this scheme. The change that we add when we want to refine a cut is that we change this 4a to also include the refinement of feasibility cats. And what the refinement does is actually solving more of these feasibility subproblems and using the information obtained from them to select new subsets to evaluate, but also to decide when it's enough, and we continue by solving the master problem. To look a bit upon the strengthening of feasibility cats, we need to think a little bit about the cat strengthening algorithms that we use and their theoretical guarantees. And to measure the strength of a feasibility cat, we introduce the notion of irreducible feasibility cats. And a feasibility cat is called irreducible if removing one variable from the cat makes the cat invalid. So that basically means that if the subproblem that is obtained by removing one variable from the cat is feasible, then that cat would be invalid. We compare 3 cat strengthening algorithms obtained from the literature that has been used to accelerate local space bending decomposition. The first 2, the greedy and the deletion filter one, relies on solving and trying to remove one master problem variable in the original feasibility cat per iteration. The greedy one tries to remove one variable in each iteration until the subproblem becomes feasible, but it has no guarantees that we can find irreducible cats. The deletion filter tries to remove each variable in turn, but re-add variables if the subproblem becomes feasible. So in this case we solve more subproblems, but we also guarantee that the final cat will be irreducible. The third approach is called the depth-first binary search, and instead of trying to remove a single index or a single variable of the feasibility cat per iteration, we choose to try to remove multiple of them, or a subset of them. But with this idea, we need to perform additional investigation if the subproblem becomes feasible to ensure that the cat that is obtained is actually irreducible. The computational evaluation that we have made is done on 3 problems with 5 datasets with a total of 2,166 instances. We have a 20 minutes total timeout per instance, and we apply the 3 cat strengthening algorithms as shown previously, together with doing no cat strengthening at all. The approach is a MIP-CP hybrid local space bending decomposition, where the MIP master problem is solved using Gurobi optimizer and the CP subproblem is solved using IBM iLog CP optimizer. And the question we want to ask is, which cat strengthening method performs best, and how does subproblem separation impact the computational performance? And I will show some plots on this first part. So for 2 of the problems, the vehicle routing and the cumulative facility scheduling, we have these 2 plots. In the y-axis, we have the percentage of solved instances, and the x-axis, the time spent for the different instances. And to the left, we can clearly see that the depth-first binary search performs best and solves all of the instances within the given time limit. The next best is the deletion filter, followed by the greedy and doing no cat strengthening at all. To the right, in the cumulative facility scheduling, where we actually perform subproblem separation, we see that there is not a large difference between the different approaches. In the third problem, the single machine scheduling with multiple time windows and sequence-dependent setup times, we have 3 instance sets. To the left is the first instance set, where we can apply subproblem separation due to the instance structure. To the right, in instance set 2 and 3, we cannot do this. To the left, we see that the deletion filter and the depth-first binary search performs best, followed by greedy and doing no cat strengthening at all. To the right, we see that the depth-first binary search performs best, followed by the deletion filter, then the greedy one, and doing no cat strengthening at all. So what we can conclude is that the depth-first binary search cat strengthening algorithms performs best across all instance sets and problems, but also that doing any type of cat strengthening is better than none. Also from the paper, we have that subproblem separation, whenever possible, has a greater impact on the computational performance than actually doing cut strengthening. That was it for me. Thank you for your attention.
Okay, thank you, Emil. So are there questions, either from online participants or from Vienna?
Nothing from Vienna.
Okay, then I guess I do have a couple of questions. Oh.
Hello. Thank you for a very nice presentation.
Thank you.
I was just curious, you might have said this also, but I might have missed it. When you drive the subsets there, have you also looked at, I don't know the right terminology there, but if you have knapsack-like constraints in the master problem, so say you have like a sum of some binary variables is equal to 1. So I was kind of thinking, because that kind of tells you that there is kind of a disjunction related to these binary variables. So I was kind of thinking if you could use that to kind of filter out like efficient subsets, so to say. I mean, there, for example, if you have, let's say you have like 4 of those constraints in the master problem, if you can, for example, then just like delete one of them, or like interm, and try to like pick 3 of those equality constraints to derive the subsets. I don't know if it makes sense or not.
Yeah, I think it makes sense a little bit. So the master problem typically have some sort of knapsack type of constraints, like, but it's more like assigning a single. You have to assign something to a facility or so on. So it's a very simple structure, but we haven't really exploited that structure when we select the subsets. So the cut strengthening algorithms, they are sort of very, very general in the way that they select subsets, and then we actually just select variables at random. But I think if you would exploit the problem structure, you can probably get some better computational performance on your specific problems. Yeah. That should be possible.
Okay. Thank you for the answer. And
thank you.
Good presentation.
Are there further questions?
Yeah. So is it on? Oh. Yeah. First one. Yeah. If it's green, then it's on. Okay, it's green, then it's on. Okay, so this is finding infeasible subsets among a set of constraints, and then you end up and saying quick explain is the most suitable. So you have a large number of initial constraints that are then reduced. So in the world of finding infeasible subsets, there are a number of techniques, for example, in the SAT community, looks at model rotation or various heuristics to speed up finding infeasible subsets. And I wonder if you can apply them to your domain here.
Yeah, so just to clarify, so in this case, there is really this connection between the variables and the constraints. So we are focusing on reducing the size of the cuts, which means reducing the size of the variables. If you, excuse me, I didn't catch the last one.
Oh, the variables select a subset of constraints.
Yes, that they do.
And you want to select a smaller subset that's still infeasible.
Yes. Okay. So then I get your perspective. We haven't looked at techniques from SAT, or at least specifically from SAT. So these are the ones that we found has been used in logis-based vendors earlier. But if you have a SAT subproblem, I guess, then you why not use those techniques from SAT instead? Or if you have an LP subproblem, you can use the specific IIS techniques for LP subproblems. But these one worked for a general subproblem.
And the other thing that's going on is enumerating multiple infeasible cores, just not one at a time, but multiple.
So what do you mean by multiple cores?
So you have multiple independent subsets that are all infeasible.
Yeah, so we are just interested in, or the algorithms that we had when we talked about the irreducible cuts, it's just one core that is irreducible. So we do not enumerate all of the cores. We just find one that we cannot reduce further. And so an additional direction would be to try to find all the irreducible cuts, perhaps, or finding the one that is the smallest, for example.
Thank you.
Thank you as well.
I think I saw a raised hand, but it was retracted, so maybe there are no more questions. So if so, yeah, thank Emil again.